Welcome everyone to the Engineering Lecture Series at the University of Wisconsin-Stout. Today we're happy to have with us Dr. Hank Tu joining us from Boston, where he works at Boston Dynamics. It's an appropriate guest for the day, given that we are wrapping up National Robotics Week, which comes to a close this weekend. So we're happy to have Hank here talking about his work at Boston Dynamics. And with that, I'll go ahead and hand it over to Dr. Tu. Thank you for
joining.
Thanks,
Evan. Appreciate it. Really excited to be here. So the title of this talk is Build It, Break It, Fix It. And this talk walks through the design process, all the way from talking to customers and trying to figure out requirements to back of the envelope concept sketches, and getting towards working prototypes. And so when Devin first kind of mentioned and asked me to do a talk, I was scratching my head, kind of trying to figure out, what might students find useful and interesting, kind of as they're transitioning from being a student to potentially a career in industry. And I kind of gravitated towards this topic. So hopefully you all take something useful away from this talk. An interesting tidbit, I actually submitted the title to this talk about a week or two before the 60 Minutes episode on Boston Dynamics aired. So by the way, if you haven't checked that out, check it out. You can find it on YouTube. But in that episode, Mark Raybert, the founder of the company, kind of mentions this phrase to Anderson Cooper. And that really reinforced for me kind of how important this philosophy is, Boston Dynamics, and how it's kind of led to a lot of the successes we've had kind of building cool robots. So build it, break it, fix it. What does that actually mean? I think it comes down to finding the unknown unknowns ASAP and then iterating to fix them. And if you kind of think about that for a little bit, that for me, that means, okay, let's find the fastest way to get to a prototype that has some reasonable amount of confidence that it'll work, so that we can begin testing. One of the challenges to this, every time is kind of determining when you've done enough analysis to have confidence, or you might kind of find a time in the design where you're spending a lot of increased time analyzing something, and kind of the benefit or the answers that you're getting with that time spent isn't really worth kind of what you're putting in. And so that's the point in the design where it's good to transition away from analysis and more towards trying to get something built and designed so that you can test it. Particularly with a lot of the things that we do, there's not really any amount of analysis or simulation that will capture everything. A lot of our loads are driven by crashes, which are really unpredictable, random, and a lot of times has to do with the surface that you're crashing into. So surface stiffness is really important, and that's really something that's really hard to model. And so, if you're familiar with our robots, we do a lot of these mobile robots. That we're really always kind of in a situation of being on the edge of over-designing. And that's a risk of losing the athletic strength to weight ratio that has been a hallmark of many of our machines. So to kind of give you a little bit of background when I started, when I first joined the company, one of the robots that I was first working on was LS3, which seems really ancient at this point. But if you're familiar with LS3, it was like an 800-pound quadruped powered by a loud and hot internal combustion gasoline engine. So, joining the company, I was really intimidated. There's a lot of cool things going on. I was fresh out of grad school, and I didn't want any of my parts to kind of be on the broken part wall of shame, right? But my perspective really changed. It was during a design review or maybe a testing field trip where Kevin, who's famously seen here, who's now probably our most infamous robot tester, said something that was along the lines of, if something doesn't break, it's probably too heavy. And that really kind of blew my mind, so it's okay for things to break? And the thinking behind it is, we're always so busy trying to design the next thing. In reality, we never have time to kind of go back and pull mass out of something that works, something that doesn't break. We're never going to go back and introduce more risk. And so, kind of the benefit of that is if you're right along the edge, you'll find out where that limit is, and then you can design just enough margin in so that your design will work and be the lightest that it can be. Now, there is a key difference between something that's poorly or under-designed and pushing the limits. And kind of as I go through this talk, hopefully I'll help you unpack kind of how to make that distinction and make sure that you're kind of on the right side of pushing the limits and not just designing something that's under-designed. All right, so I'll frame this talk in the context of Atlas. Atlas is our humanoid R&D platform. Kind of the most common analogy for Atlas is that it's like a Ferrari or a race car. It's pushing the limits of strength to weight, of performance. And we're not kind of constrained by costs or other considerations that you might have to think about if you're designing a product for high volume production. So Atlas is electrically battery powered, but hydraulically actuated. It's got 28 degrees of freedom. The robot itself stands about 1.5 meters tall, weighs about 80 kilograms or 175 pounds. It's got a full computer stack in it with 3 CPUs. That does all the onboard controls for all the limbs and placing the feet and the arms, figuring out momentum in the robot. And it also has a LiDAR and stereo vision sensor suite kind of in the head so that the robot can kind of sense its surroundings and make smart decisions about what the situation is. And I've kind of highlighted or bolded some of my designs that are on the robot. The most recent one is this high power impact safe battery that went on just earlier this year, just prior to the Do You Love Me video. So that battery kind of enabled some of the longer, more kind of athletic dance moves that happened on that video. So that was really cool. And another one of my big designs was the modular integrated hydraulic power unit, which is, as far as we know, one of the most compact, power dense HPUs on the market right now. The pelvis was a really cool design as well. A lot of really tightly integrated mechanisms, a lot of 3D printed parts, topology optimized parts, printed manifolds. I've done a lot of that, and also the feet. It's kind of my one of my favorite parts. Probably my oldest part that's on the robot right now. It's been in service since 2015, and we haven't broken actually any of the machine foot structure, so it's probably too heavy, as I just said. But my point in pointing out some of these projects is just to build up a little bit of street cred. I've designed 1 or 2 complex things in my career so far, and I just want to highlight that the process that I'm about to share with you all, is really instrumental in kind of leading to success. So this stuff really works, and I hope you can incorporate it kind of into your design process as you take on jobs in industry or in academia. All right, so back in 2018, I was issued a challenge by the Atlas team, and that challenge was to increase the hip strength by 2 to 3 times. While staying mass and volume neutral. And that's really a key requirement there that made the design really hard. And oh, by the way, while we're redesigning this, let's increase the range of motion by 1.5 times while you're at it too, along with all those other things. So if I kind of show what the robot looked like prior and after that upgrade, kind of see the pelvis highlighted there. And you'll see that, hey, we got 3 times the strength in the Z direction, and we hit that 1.5 times the range of motion. And we also got 2x in the X direction. And kind of to spill the beans here, this isn't a coincidence that the final design kind of met these design metrics. And, you'll find out why as I go through this talk. So how did we do it? Well, unfortunately, the answer isn't magic. Or maybe it's not surprising that it's not magic, but instead this really methodical design process. And I'll kind of walk through kind of each of these steps as I go through the following few slides. So the beginning of any design is defining the requirements, trying to figure out what am I actually designing. And the key part of this is to talk to customers, talk to stakeholders, talk to your business developing and marketing team, try to figure out what this thing needs to do. And in the context of this pelvis design, that was really driven a lot by the controls engineers. This was prior to when we started doing all the parkour kind of behaviors that you've seen on YouTube recently. And so we needed this like 2 to 3x in hip strength to do those types of things. That mass and volume neutral requirement is very important. As things get bigger, they tend to lead to more interferences with the limbs as the arms and legs are doing things and moving through space. If we pick up a lot of mass with this upgrade, then we're kind of losing that strength to weight kind of advantage that the new design was supposed to do. And then there are a couple of other key requirements that were kind of just brought along for the ride. You know, the previous design had a spherical hip. It also had a relatively flat torque curve. You know, those things are kind of controls conveniences that the controls engineers really wanted to maintain. And then there's additional ask from the team lead, and that was to keep the existing interfaces. You know, make sure that the legs can and the torso can still bolt to this new design without having to redesign those things, because then, you know, if we didn't keep that backwards compatibility, then that would lead to a design spiral, and we simply didn't have enough people to kind of revisit all those interfaces. So hopefully that gives you kind of a clear picture of, you know, how focused the requirements were for this design. And once you have the designs or the requirements figured out, you know, the next step is brainstorming. And for me personally, this is like, you know, the most fun part of the design is just thinking and trying to figure out, you know, some cool ideas for how to achieve or how to solve the problem that you're looking at. And one thing that I want to point out here is, like, when you're beginning this, you know, no idea is too radical. Just get everything down. You know, it's like the writer's block analogy. Don't think too much about if it's a good idea or a bad idea. Just write it down. You can always sort through it later. If your company allows it, you know, look for inspiration from prior art. Look at patents. You know, see what else is out there. You know, maybe someone's already solved some of the pieces that are involved in your design. And if you're stuck, you know, move on to another part of the problem and circle back, right? And so some of the common tools, you know, that I use when brainstorming, you know, pencil, paper, napkins, you know, notebooks, you know, try to make it as easy on yourself to get your ideas kind of documented so that you don't forget about them. Another thing that I found to be really useful is, you know, PowerPoint, Google Slides, you know, taking screenshots, marking them up with some simple sketches to kind of convey ideas. And every once in a while, you know, CAD is also very important. You know, sometimes things are very tight fitting, or you want to see if a mechanism is moving the way you think it is. You know, so CAD is also very helpful in this kind of brainstorming process. Now, one question I think that's really hard is, how do you unlock the creative process? And unfortunately, I don't have a good answer to that one. But, and you know, this is your first top tip here, is, you know, it really helps to break big problems down into smaller ones. And I can almost guarantee you that if you do this enough, you'll eventually get to a small enough problem that will be, you know, manageable in terms of solving. And kind of once you solve that innermost layer of the problem, you kind of move on to the next ring, right? Make that problem a little bit bigger. Okay, what are the next challenges? You know, and just work your way up until eventually you've kind of covered all those smaller design challenges and kind of have looked at the whole picture. So going back to the pelvis design, you know, here's an example of how we kind of broke that down. You know, so there's many degrees of freedom in the robot. The pelvis has 5 of them. So okay, so we said, all right, let's pick one of them. So let's start with the hip X mechanism. All right, so, you know, there's a lot of different ways that could look, and you know, so that's kind of intimidating. So what we said was, okay, well, we know Atlas is hydraulically actuated. What's the simplest hydraulic piston, right? So if we start with a building block and make that as simple as compact as possible, you know, that'll then spiral out and make the whole design more compact. Well, there's a lot of different ways that can look. So then we broke that down further. Well, what's the simplest hydraulic piston seal arrangement? And if you look at a lot of hydraulic actuators on like industrial machines or traditional mobile hydraulics like excavators or backhoes, you know, they have a seal stack. You know, they have multiple redundant seals. And a lot of this is to prevent leakage, right? So if one seal fails, you have another seal, you know? And so, you know, for Atlas, you know, we obviously can't tolerate a large leak on the robot, but a little bit of weeping or a few drops here and there is okay, because it's an R&D machine, you know, it's in the lab, it's not going out in the real world. Our customers are the controls engineers, and so they can live with that. So once we kind of thought about that, we're like, okay, well, is one seal enough? And the answer to that question is yes. So once we knew that, you know, one seal is enough, that led us to kind of designing the smallest, you know, simplest piston, and that in turn allowed us to design the most compact hip X mechanism. So that's just an example there. You know, you can apply this to almost any design problem that you'll see, and it'll definitely help you get unstuck and kind of move along the design in terms of solving the bigger problem. Okay, so once you have, you know, some concepts, you know, a key thing to do is to eliminate the weaker concepts ASAP. And so if you're having trouble proving whether or not a particular concept will work or not, well, maybe another way to look at it is to see if you can prove that another one will fail. And this is kind of a thought process that we picked up, while we were part of Google X, around 2014. Google bought Boston Dynamics. After a little bit of confusion, we were kind of put under the X division. And this is what one of their kind of guiding principles is, hey, try to find out, how quickly can you find out that something will fail? And if it turns out that it will fail, then don't spend any more time or resources carrying along that concept. Focus on the ones, that still look promising, that still have merit. Okay, so once you have a couple of concepts that pass the sniff test and look like they might be promising, the next thing to do is really take a quick first pass at sizing and analysis, just to see if things will still work. Does it still have merit? You don't really want to spend a whole lot of time really digging down at this point in the design phase. You just want to use simple equations, use the textbook equations that you've learned here at UW Stout, like in your engineering classes. That's the type of level that you want to do on the first pass, because you want to find out as quickly as possible, which ones don't work and which ones still have promise. Important things to think about: inertia, stiffness, strength, maybe contact stresses, maybe it's just some basic bearing analysis, like, well, what do the bearings look like? Are they going to be too big? Natural frequency. So, kind of parameterize your design or the different concepts kind of in the same way, kind of apply the same kind of equations to them and kind of see how they shake out relative to one another, and only add sophistication to the analysis if you really need it to try to understand risks or holes in the design. Another top tip related to that is to create your own design tools. We do a lot of MATLAB, spreadsheet type things. One of the real benefits of creating your own tools is that you understand what is being modeled. You know what all the assumptions are. You're not working with a black box and trying to figure out, all the things that are or are not included. And what this helps you do also is to develop design intuition. So on this pelvis design, I wrote a MATLAB script to help me size different mechanisms. That was a lot faster than trying to go through SolidWorks and using the kinematic tools there to see like what the torque curves were. I could just change a parameter, hit run, see what it looked like, and that really helped me develop a lot of insight into how to lay out kind of how these mechanisms should package relative to one another. Another really important thing about these simple kind of analysis tools is that it really helps you sanity check your more sophisticated analysis down the road. So if you're doing FEA, and there could be a lot of issues with that, garbage in, garbage out. So you really, as many checks as you can kind of incorporate to future, more complicated analysis, the better. Helps you build confidence in that what you're looking at is correct. And another benefit is like, if it's a tool that you created, you can probably do something like wrap an optimization loop around it. So, things like that are really hard to do if the core piece is a black box. So, really highly recommend creating your own design tools when approaching a design. And that relates to this next top tip, which is to sanity check your results. So, something that I always do when I'm working through equations is checking my units. Is that consistent? Does power in equal power out? Do I have conservation of momentum, conservation of angular momentum? Like the more things that you can just kind of check along the way, the more confidence you build that what you're doing is correct, and that if you're using the results of these analyses to drive your design, that your design is correct. Another example of that is FEA, right? So let's say we're exploring the strength in like a really complex organic hydraulic tube that's in the manifold of the robot. Start with simple hand calcs like a thin-walled pressure vessel, hoop stresses, right? So start with something like that. Then as you start your FEA, try to pick out like a straight-ish section of that long line and just see, do the stresses there match your hand calcs? If not, well, maybe your assumptions are wrong. Maybe I need to look at the thick-walled pressure vessel calcs. Or, maybe there's a problem with my analysis. Maybe my mesh is too coarse, right? So lots of things like that. Just always check your work. Always make sure everything's consistent. You really need to build confidence, in this stage of the process. Otherwise, the things that you're proposing, won't work the way you expect. And now here's a quick aside on maybe one of the hardest parts of the job. and that is to not be attached to your own concepts or ideas. And this is hard for everyone because everyone wants to see their idea, end up on the robot. But really the danger here is, holding on too long to unsuitable concepts. It wastes time and resources that are better put on a more promising design. So it's really important to be objective and honest when evaluating ideas, especially your own ideas. It saves you a lot of headache down the road. So yeah, don't hold on too long if it's obvious that your idea, maybe isn't the right fit, and don't go down the wrong rabbit hole because you're going to end up being late to getting your design kind of in the hands of your customers. All right, so we just did all this work. We have hundreds of napkin sketches of Rube Goldberg devices and MATLAB scripts to size all of them. Well, what do we do if none of these concepts meet the requirements? And kind of the tongue-in-cheek answer to that is we change the requirements, right? But it's not as simple as simply crossing off the requirements that you don't like or that don't fit. And so kind of my experience has been that, in the initial requirements defining stage, that's kind of like the kitchen sink. It's not just the kind of critical must-have requirements that are included, but there's a lot of nice-to-haves that other people might want that maybe aren't absolutely necessary, but kind of get bundled in initially. And it's these like design challenges as you're going through like this first kind of pass analysis stage that kind of forces some difficult trade-off discussions. And you really need to evaluate as a team with all your stakeholders, like what features are must-have and which ones are nice to have. And when you start looking at the nice to have ones, which are the ones that we can eliminate in order to get a design that fits, right? And so one thing to keep in mind is that, every single additional requirement that's baked into design, has some overhead and penalty to it, whether that's mass, volume, cost, complexity, or lead time, or reliability. Every single feature adds something, and that's something that you have to carry throughout the whole design process. So knowing which ones that you can eliminate and getting kind of buy-in and agreement from the whole team to do that is really challenging, but it's very important to get kind of the most suitable design at the end. So if we circle back to this pelvis example, I got the initial list of requirements on the left of the screen here. And you can see that there were two that we were able to change. One was that spherical hip requirement that was a carryover from the previous design. And so by kind of adding offsets to some of the different joints, we were able to, it allowed us to use a different class of mechanisms inside the pelvis. So the cost of that came with controls complexity, and we really needed to get buy-in from the controls team that was okay. So it was kind of like, well, do you want this strength, or are you okay with this complexity? And at the end of the day, they were okay, willing to take on the extra complexity on their end in order to get the extra strength that they required for the new behaviors they were developing. Another one is that flat torque curve, which again was a characteristic of the old design, but by kind of revisiting that one, we were again able to explore different types of mechanisms. And again, that ended up being worth it. So, by not having that, we have joints or actuators that are oversized in certain parts of the range of motion, that leads to less efficiency, more power consumption, and also more controls complexity. But to enable us to get the strength that we needed, that was a trade-off that was worth taking on. All right, so once we have one or more concepts that meet the agreed upon requirements, then we move on to detailed design. And this is what detailed design looks like, at least in my opinion. So you kind of start off with detailed analysis, and that's where you'll do stuff that you might be a little bit more familiar with, like FEA. Also important to identify any holes or risks in the design. Kind of once you have those things figured out, it's really important to think about DFM, DFA, design for manufacturability, design for assembly, making sure that your design can be made real. Kind of once all those things are you have a good idea of those, then it's really important to have design reviews to get a larger audience to kind of poke at your design and look for holes or risks, and then build a prototype. So let's talk about all these things in a little bit more detail. So in detailed analysis, it's really important to get the details right. And there are so many different types of details to get right that, this is a really big challenge of any design. So many things to consider, like, for example, thermal expansion, like will your design seize when it gets hot or leak when it gets cold? Cable routing, if you don't think about that and you have a lot of dynamic cable bending, that could be a failure point that could lead to a lot of pain. If that's a common issue and if cables are buried deep in the design and are hard to access. Other things that are important, galling hardness. If you don't pick the right materials, you can have things that gall and seize as you're just threading them together. So these are all things that are super important. A lot of these come with experience. So, if you're looking at design and you're not sure if you can answer the question yourself, don't be afraid to ask for help. Seek out, more experienced coworkers. Sometimes component vendors, like bearing manufacturers, for example, can help out with more detailed analysis. So don't hesitate to reach out to vendors for advice. And the real key point here is that you might have the most clever design in the world on paper, but if you don't get the details right, it's not going to work in real life. And as the saying goes, the devil is in the details. So after you've done some analysis, taking a closer look at some of your concepts, you really need to plug any holes that turn up during that phase. Whether that's with rapid prototypes, getting some things made physically so that you can see how things fit together, or if they will fit together, or how they move. In our current modern era of design, where 3D plastic printers are really common, take advantage of that. And if there things that do come up that you find during rapid prototyping, go back to brainstorming. Is there a way to solve it with your existing design with some tweaks? Or if not, maybe it's time to go revisit those requirements and to see if there's anything else that you can relax to make the design feasible. One common hole for many people is DFM. So really don't forget about machinability, assemblability, or serviceability. Ask questions like, can it be made? How much are the machinists going to curse your name as they're trying to make this part? Can it be put together? How much will the technicians be cursing your name as they try to put this crazy complex thing together? How hard is it to fix if something breaks? How much will the service team be cursing your name as they have to take this thing apart to reach something that's really buried deep in the design to get it working again? So hopefully you're seeing a common theme here, and that's that a bad design leads to a lot of cursing, and thoughtfulness upfront in the design to address machinability, assemblability, serviceability really makes many people's lives much easier down the road. So rapid prototyping, again, is a good way to kind of find this out early before you actually get parts cut out of metal. Another thing is just to kind of go along with what I said earlier, is just to be a good citizen. Really think about in advance your coworkers' well-being. Don't be that engineer that no one wants to work with because your designs are so hard to build and put together. One thing that I've learned is that reputations really stick. Like when we were a smaller company and there were less mechanical engineers on the teams, it was kind of easy to look at a part in CAD or look at a drawing and to kind of know whose part that was. Everyone's fingerprints are kind of on their designs, whether it's how they model the part. Some people like to use a lot of fillets. Some people don't use any fillets. Some people have weird transitions between different features, and some people are really good at designing beautiful parts. It's all part of how we think and kind of our experience. But those kind of traits, I think stick in people's minds and kind of gives you a reputation. And just to kind of give you an example that happened recently to me, I was meeting with, so we have an internal machine shop. I was meeting with some machinists there with a couple of other engineers. So we're designing some parts in an arm assembly. And, we had some common features. So as we're going through kind of the concerns of the machinists, they come up to this 4-micron perpendicularity tolerance. And immediately all of the machinists point their fingers at me like, Hank, is this you? So I had this reputation being on Atlas of really calling out tighter tolerances because, we're R&D we're not creating a lot of things, or just a handful of parts. We want to make sure that everything fits together and works. And so we always tend to err on the side of tighter tolerances, which is different from a production standpoint. If you're designing a product, you want to relax the tolerance as much as possible so that your yield goes up, right? So that's kind of funny. I was actually framed in that particular example that perpendicularity callout was actually specified by the bearing manufacturer that we're using. But again, reputations, they're around. People are going to have that kind of bias in their minds. So make sure your reputation is a good one. And another part of this is that, at Boston Dynamics, many times the engineer who designs the assembly is the first one putting it together. And I think that's really important too, because that really teaches you kind of, hey, is what I thought in design, does it actually work that way in real life? And you'll really learn a whole lot from that process. So I encourage, all of you, if you have the opportunity to kind of build the first prototype of your design, do that. You'll learn a lot from that process, and it'll carry on to a lot of your future designs. So you might be asking yourself, well, how do I avoid all that cursing in the future, right? And that leads to this next top tip, which is to get your hands dirty. And so, this is a lot of words. So I'll kind of walk through this a little bit and kind of my thinking behind all these different things. So awareness of cool tools. As you, let's say, pick up some hobbies like working on bikes or cars, you'll get a sense for what types of tools are used to reach hard to reach places, or what kind of torquing features are available. Like, when is it better to use an internal hex versus an external hex versus a Phillips? There's all those sorts of things that you'll kind of gain experience with as you're working on someone else's design, a design that's already out there, a product. It's really important and really interesting to kind of see how someone else designed something, and what can you learn from that and kind of implement into your own designs. Another benefit is, as you start working with your hands and working with tools, you'll get confidence in building new things that have never been built before, like your first prototype. That'll really help you understand how things go together and how they come apart. And that will help you plan for assembly and service from the beginning, which will make your technicians and service teams' lives way better. So, really, really try to do this. Another thing is, something I've had to do more of is writing documentation, like getting used to reading repair manuals for cars or other things. That'll help you learn, like, what's a clear way to present how to put something together or how to take it apart. Other things like learning how to machine stuff. Like, if you have a prototype part come in and something got missed and doesn't fit and you need to do a quick mod, if you get some experience with like mill, lathes, machining, like that'll help you work around, surprises that come up. So there's really many benefits here. There's too many to list. I encourage anyone here, everyone here, to really get your hands dirty. Doesn't matter what it is, just start tinkering with stuff. And really, it's never too late to get started. So as I'm thinking back, giving this talk, when I was a senior, undergrad at Penn State, I really, up to that point, hadn't gotten my hands dirty a whole lot. It wasn't really until grad school where I started, doing more. So one story is bikes. I moved to Minnesota to go to the University of Minnesota, and biking is huge there. And so that's, my when I first started, I got my first, bike shop bike. It was a giant mountain bike. I still have it to this day, but really learned how to work on bikes and all the tools involved. It's like 15 years later, that bike has like 8,000 miles, but every time I give it a tune-up, it rides like brand new. So, really, you can learn this stuff, and it doesn't take a whole lot of time to do it. And the other thing too is, in the lab that I started out with, we really didn't have any money. So we didn't have money to send parts out to machine shops for fabrication. So I had to kind of work in the student shop at the U of M. And I learned so much from all the cranky old machinists who ran the shop there. So really, it's not too late. If you haven't gotten really your hands dirty up to this point, you're in the same boat that I was in like 15 years ago. Just get started now. It'll make your design life and your future career as an engineer way smoother. And this last phrase here, I kind of adapted a thought from Michael Hammond, who gave a talk in this lecture series a few years ago on industrial design, is that, great mechanical engineers think like machinists and technicians. The more you can think about how a part is going to be machined how it's going to be put together, that will really take your designs to the next level. Okay, so that, a related note is another important thing is communication between disciplines. This is said a lot. Robotics is a team sport. There's so many different types of disciplines that are involved, and it's really important to really maintain good communication with all these different parts of the puzzle. So to give you all a few stories here, so on this pelvis design, I work with Bill. He's one of our mechanical technicians. I used to be a race car mechanic. Is a awesome fabricator. So we were working on the assembly of this pelvis, and so I had this idea in my head, like, okay, there's one mechanism's kind of buried into the design. If we kind of have enough access, we can kind of populate this pin on the inside through one of the bearing bores on it. And so we talked about this. I had it in my screen, took like measurements, move things around, looked great, right? So when the parts came in, I hand them to Bill. He works his magic, and a few hours later we have a pelvis. So I go back to him and I say, hey Bill, be brutally honest here. How did it go together? And he's like, dude, like if you do it this other way, you do the pins first, and then you have these things, and then put these things on last. Like it's so much easier. And that blew my mind. It was like, I would have thought that way would have been impossible, but he's been working with engines and gearboxes. Like he just found a way to just make assembly not even an issue. And so like I love that example because we're good at what we do as mechanical engineers, but I'm never going to be as good of a technician as Bill, right? And so learning from him, leveraging his experience, and incorporating that into future design is really key. So yeah, this is very important. Another story is just recently I was working with Arjun, who's an electrical engineer, and so we're trying to make this electrical connector fit in something. And so I was like, okay, well, what if we shift the board this way a little bit or do that? Trying all these different things, cutting a notch here to try to make this clear. He's like, well, if I make the board wider, does that fix your problem? And yes, done. So easy. So really just keep in touch with all the different people on your team. There's a lot of things that they're thinking about that you're not thinking about, and really that can make problem solving a lot easier. So super important. And kind of to play off of that a little bit, cross-team design reviews. That's one of the, I think, really key things that leads to successes at Boston Dynamics is that, we get feedback, at kind of gated parts in the design to get a much larger group of people together to kind of look closely at design, try to find holes. And really, everyone has their own kind of specialty and experience, and that is really beneficial in terms of just looking at a design from a holistic standpoint, and just making sure there's nothing that you as a mechanical engineer are missing. So some important things here, is give reviewers enough advance notice so that they can do their homework ahead of the review. Give them the slide deck or the part number in CAD of your design so that they can kind of take a look and kind of think about things a little bit before the review. One other important thing is to make sure you hold the review before it's too late to make changes. In the past, there have been times where, we would have a design review, and some of the parts had already been sent out for fabrication. And so at that point, it's really too late to make changes, and it's probably too late for a review. So really hold a review kind of as early as possible, and take that feedback to make your design better. Okay, so we just finished the design review. It's time to build it. Get that prototype as soon as possible. And some points that I had mentioned earlier is know when a design is good enough on paper to make it real, because you're going to learn so much more quickly by just having that prototype and then being able to test it. So again, leverage 3D printing, leverage First Cut or Protolabs. A lot of the times, First Cut parts are pretty good, and you can get a lot of mileage out of them. We have this joke in-house of Second Cut, right? So you get your First Cut part, but it's missing some like key tolerance features. Well, you can post remount holes for pins or things like that. So First Cut can get you most of the way there, and then just do a little bit of extra work to make it something that's actually usable. So that's really a key thing that can really accelerate your prototype making process. All right, so we're at build it. All right, now we're at break it. Test things to the limit. and find the unknown unknowns, and make sure you're testing the right thing. Sometimes early on, we don't have the whole robot, so we design a piece of it, and then we create a test stand that tries to mimic its use case as closely as possible. So, if you don't have the whole thing, break it up into a smaller piece, test that, make sure you're testing the right thing, and learn from it. Here's what a typical day at the office for Atlas looks like. So I'll play this. Hopefully the sound works. Yeah, so I'll let you use your imagination to see how that last fall ended. Needless to say, it was pretty epic. But yeah, so we aren't kind to our robots. We put them through real world testing, and we try to learn as much of it from it as possible. And so that's why we have a world-class technician team to fix things when they break. We're not afraid to break things, but we do try to learn from things that break and incorporate that into the next design. And that leads us to fix it, which is iterate, 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 iterate. And the important thing here is to really identify the actual root cause. It's really important to understand why something failed and how it failed. And I think the key here is that many quick iterations, at least in our experience, is much more productive than a single extended design cycle where you spend too much time even on the analysis phase and don't really have many opportunities to learn from just the testing process in the real world and finding those unknown unknowns. So I think I have a little bit of extra time, so I'm going to go on to a bonus section here, and that's just a little bit of career advice for those of you who might be curious. So put together a few thoughts about transitioning from school to industry. Besides working hard, I think a really important thing is to don't be afraid to ask questions. And also to be honest about your skills and abilities, but trust your gut, right? So, just because someone has 10 or 15 or 20 years of experience doesn't mean they necessarily are doing things the right way. They could be, have a lot of many years of bad habits, right? So, trust your gut. If something doesn't feel right, it's probably not right, but, be teachable, have an open mind, be open to learning new things, or maybe doing something that a little bit differently, like maybe you'll find a more efficient way to do something that you've done before. So try to learn as much as you can from your coworkers, look for opportunities to keep expanding your engineering tool belt, because all the different things that you learn, I think, will help shape your future designs and help you produce higher quality designs down the road. Learn from your experience. Related to some of these other things is, admit when you don't know something. I'd much rather someone tell me that they don't know how to do something than to try to fake it and get it wrong, and then now you're many weeks into a design when you could have avoided that from the beginning. So really be honest about that. Your coworkers aren't going to expect you to know everything coming in, so just be honest here. Another thing is look for a mentor. Maybe someone you connect with, like from a hobby or something else. Look for someone who isn't your manager, who's willing to help you get up to speed and kind of teach you some of the things that you'll learn as you kind of develop your career. Along with getting the details right, yeah, be rigorous about that. That's super important. As engineers designing mechanical things that are in the real world, we need to get those right. Otherwise, it's not going to work. So if you need help, ask for help. If there's something you're concerned about, bring that up. You're not expected to solve everything yourself, but identifying kind of what the important things are and identifying things that maybe aren't right is super important. Taper this down, but act with professionalism, respect your coworkers, and safety first. Like if you're in the lab, you're machining stuff, make sure you're working in a safe way and that you're keeping your safety and your coworkers' safety in mind at all times. All right, and then the last thing I'll talk about is a note on work-life balance. I don't think this really gets brought up very much. I think this is super important. I think everyone needs to find a balance that's sustainable for them. Hopefully by now, after having been in school for a few years, that you realize that your mind works better when it's fresh. So don't just work more, but instead work more efficiently. I think that's really important. Don't burn yourself out. We're all in mechanical engineering because we love what we do. Make sure that you're able to sustain that in the long term. So you have a long career designing a lot of cool things. I think it's also very important to nurture hobbies, passions, and interests outside of work. Stay happy, stay healthy, have a good mindset. I think that'll lead to more creative, better designs. And, this is just a little bit of a warning, but, even companies that promote balance don't make it easy. There's always aggressive schedules, one aggressive schedule after another, nothing. So it's really on you to kind of make sure that you are strict with work-life balance and find something that'll work for you so that you don't burn yourself out. And so I will end there, and I'm happy to open it up for any questions and some discussion. So maybe I'll hand the mic back to Devin.
Well, thank you so much, Dr. Tu, for your presentation. Let's take a moment to unmute our mics and thank our speaker for being here with us today.
My pleasure.
Thank you.
To be honest, I'm patting myself on the back right now for inviting you to come as a speaker, because that was really an incredible presentation, especially for a group of mechanical engineers to hear about. And I don't think I'm exaggerating when I say that, myself and others will probably refer to this video and use it with our classes and our students in the future, because you really touched on a lot of points that, that we think about all the time, and the things that, engineers need to know as they prepare for their careers. And I think that this was a really valuable, succinct way to kind of put all those things together and say, literally, here's how you be an engineer. And I appreciate that. So thank you so much for really a great presentation.